Okay, we have now, I think, a quorum of people joining us for this webinar. Thank you all for taking time out of your busy days to join us for this webinar entitled Benefits of a Standard-Based Approach to Distributed Acoustic Sensing Data Management. As usual for our webinars, we will not be entertaining any questions during the presentation, and we would ask you to put all your phones or audio systems on mute. Please use the Q&A button to submit questions and answers. At the end of the formal presentation, we will address those questions live as part of the webinar. This webinar is being recorded, and you'll be able to access it on our website probably sometime tomorrow. And there is a survey at the end that we would kindly ask you to quickly answer, just a couple of questions that help us orient our future presentations. So today we will have two speakers. Wilfried Belin of Shell will be driving most of the presentation. Lawrence Omerod, who is a PRODML project manager, will be joining us. He's currently in another meeting, so he could be a few minutes in joining us. However, we're not going to hold you up any longer, and we're now going to start the actual presentation. So maybe Jay, if you could take the next couple of slides, which are an introduction to standards. Hi, Lawrence, good morning, or good afternoon. You need to turn up your volume. We're not hearing you very loudly.
Okay. Can you hear me through the handset?
Yeah, that's better.
Okay.
All right.
So do you want me to present these, or do you want Jay to deal with them?
Jay can take this one, yeah.
Oh, okay. So we hope you guys are familiar with Energistics since you've dialed in to the webinar. And as you know, Energistics is focused on developing data transfer standards. We aim to cover the entire breadth of upstream. And so in that context, we have the most famous one is WITSML, which moves a large portion of all the real-time drilling data in the world. It moves. But WITSML isn't just about drilling, it's also about the well. So anything to do with the well itself, including its construction, is generally handled in WITSML. Then we have PRODML, which is the production aspect of our transfer standards, and it covers a wide range of things from PVT analysis, monthly production volume reporting, partner reporting, describing the interconnection of the field facilities, just pressure as a new model that's just been redesigned for all kinds of well testing based on some collaboration between Schlumberger and Kappa Engineering for pressure transient analysis, and I've left a lot of it out. But the thing we're here to talk about today, of course, is distributed fiber sensing, and we have the two standards that the industry uses for distributed temperature sensing, and today we're going to be talking about distributed acoustic sensing. There's other fiber sensing like strain sensing that if the community desires, we could move into that. And finally, you have RescueML, which is a way to transfer data between Earth modeling applications, seismic through to simulation. Anyway, so that's in that domain. So I guess, Phil, we can just
Wilfried, next slide, please.
Is there an animation on this one?
Wilfried, could you click the next tag?
Right, and so the point of this little animation is that in bygone years, these were three really independent standards, but now the work that we've done over the last few years is to sort of merge them together in one big, you can think of it as one big standard. So if you need a well when you're doing production stuff, you can use the WITSML well, or if you're doing some Earth model movement and you need to know production history for a reservoir simulator, you just use the PRODML object. So you can think of these all now as one standard without boundaries. And with that, I guess I'll turn it over to Lawrence or Wilfried. Oh, so I've already mentioned this actually, but in the PRODML, what PRODML is for, as I mentioned, is volumes reporting, which could be either sort of the volumes reporting that you do, to operating partners, or there are some places like Norway that use PRODML as the way you report, the standard way you report, actually to a regulatory authority. I mentioned PVT analysis, and that obviously covers the whole breadth of that. So that includes the acquisition that you do of PVT samples in the field, the way the samples are handled, the bottles that the samples are placed in, the analysis that happens in the lab, and then the overall fluid characterization. And what we mean by that is, you grab some samples from a reservoir, but at some point you want to characterize based on what you've seen at the surface from a variety of wells, what's the characteristics of the overall reservoir fluid downhole. And that's a kind of a separate process, but we cover all of that. I mentioned the production tests and pressure transient analyses. We also cover wireline conveyed formation testers. Have a special model for that as well. And I just said also, you can describe the piping network that you have in the field. And separately, you can also define of that piping network, what is the actual hydraulic network? Because if some of the valves are closed, then there may be pipes, but there's no fluid flowing through them. So what's really important to know is what's the interconnectivity of the flowing lines I have in a field gathering system. And so you can describe either or both of those with PRODML, and then the DTS and DAS exchange standards.
Okay, thanks, Jay. Yeah, so let's have a look at the distributed acoustic sensing data exchange use cases. So distributed acoustic sensing has been started to gain traction in the oil and gas industry in about the last 8 to 9 years. And we've seen a number of applications being developed. There are quite a number of applications that you can run using distributed. That you can use with distributed acoustic sensing along a fiber on a well. And so here at the bottom you see a number of these applications. And I think what's important to remind people of here, there are quite a number of applications that you can run during the life cycle of the well. And basically these can be divided in broadly 2 types. So we have more specialistic in-well monitoring applications, and we have seismic surveillance applications. Both basically originate or can be processed out of both can be processed out of a DAS data set, and typical examples of in-well monitoring applications are hydraulic fracture monitoring, where you basically use the noises to understand how you place fracture in the well. But you can also say something about zonal injection and production. You can look at artificial lift. You can also see before and after you have stimulated the well, the differences on a DAS display, and basically create some diagnostics about the efficiency of the stimulation. So for the seismic surveillance applications, things that come to mind are VSPs, vertical seismic profiles, and also it's a more complex application, but it's also gaining some traction in industry, is microseismic and strain front detection, which can be used is used at the moment typically with hydrofrac jobs. Now, why do we need a data exchange standard? The amounts of data that DAS can generate is enormous, at least at the well. So a raw data set, so an interrogator collecting data from a fiber, can be about 1 terabyte or more a day. Now, of course, we don't always exchange or transfer all that data. So typically there's some processing taking place that, for example, filters frequencies, or people use some kind of mathematical transformation, like a Fourier transformation or another transformation, to create a spectral plot of the data, and then that downsizes the data to megabytes or gigabytes a day. And for that type of data, that's what we have defined an exchange standard for, because when we started on this journey about 10 years ago, then most DAS providers provided binary data sets, and these are notoriously difficult to handle because every vendor had their own format. You had to write custom software, and that basically, it's very cumbersome, and I think everyone here on the call understands why we need standard. One thing to explicitly mention here is that, so this exchange standard is for raw and for process data, but when we talk about end products, for example, SegY for seismic traces, then typically people will get that distributed in the format that is already common in industry. So if you exchange raw data between an R&D outfit and a DAS provider, then they will write some code, but if they then distribute the SegY data, they'll do that in SegY itself and not distribute the DAS data. Okay, so basically, I mean, why did we start on the journey for an exchange standard? So in my company, we actually spent lots of time and we took lots of effort to basically write all these codes for the different type of DAS data sets we got from vendors. Just to give you an idea of the cost of that, we probably spent more than $500,000 internally to write all these scripts to cater for these different standards. Now, so it's expensive. Not having a format, and that's just an example of one operator company. Also, there's a lot of non-productive staff time. In the initial data sets, researchers were actually spending weeks to convert these terabytes into something useful that they could analyze. Well, because it takes a long time, I mean, if you do a hydroфрак job, you're not interested in getting a data set 3 months after the job. You want to get it relatively quickly. And so basically, delayed decisions, and that also then leads to missed opportunities, and it diminishes also the confidence. Say through the grapevine, we heard stories of people acquiring DAS data, but then because they couldn't read the format or were not able to process it in time, the value was not recognized. Let me see, I'm going to bit of chatter on the line. Anyway, that leads to slow uptake in assets. Basically, it's complex to share data with other parties, not having a format because everybody needs to write these codes, or you need to exchange software to read and write data. And also what we really aim to do with an exchange standard is to create a model where, say, any party that can provide a service on DAS data or is interested in working with it can actually develop on a common standard, and thus we create a kind of a framework where people can develop tools and and basically go from there. Sorry. So I think the need for an exchange standard is obvious. Okay, then, what is what does the data look like when you create a DAS measurement? Let's first talk a bit about the system. So the system typically consists of a fiber in the well, which is here you see a very rough schematic of a well, and so you have the green line is the fiber in the well, and you see some dots along it, which are positions at which the DAS system measures. There's also typically some splicing at surface to connect it all the way to DAS interrogator unit, and the unit is then of course the measurement system that sends out pulses and then collects the data. On the right-hand side, you see a bit of a schematic representation of what the data would look like along the basically the service fiber plus the fiber in the well, so the full fiber optic path. And then just to give you an idea of how the interrogator basically collects the signal. So here you see a video where basically a pulse is shot in the fiber, so-called uses coherent OTDR, optical time domain reflectometer technology. The pulse propagates along the fiber. Impurities in the fiber cause so-called backscattering. The backscattering is measured, and that's what you see on the left on the detector signal. So it basically collects the backscattered light from the pulse over a certain amount of time. The time is representative for the location along the fiber, because the farther away, the longer it takes for the backscattered light to come back to the detector in the DAS unit. And so what you see here on the plot on the background, so the highlighted vertical column, that's basically one measurement where you shoot one pulse in the fiber, and then you basically record the backscattered signal. And then because we the DA converter sample with a certain speed, you basically get a set of samples along the fiber. And then for each pulse that you shoot in the fiber, you basically create another column, and the rate of interrogation of these pulses, I think typical up to 50 or 100,000 pulses per second. So you can see that the amount of data collected can be large. Typically, say along a 1 kilometer fiber, we have say a few hundred to 1,000 or even 1,000 plus channels. So if you have a fiber of a few kilometers in a well, you have thousands of channels, and each pulse will create a measurement that contains all these thousands of basically measurements along that fiber, and that happens up to say 100,000 times a second, depending on your pulse rate. So the volumes can be very large. So that's how the raw data measurement may collect up to 1 terabyte a day. What you see here on the screen is a downsampled plot of such a DAS measurement. So on the vertical axis, we basically have depth along the well, or travel time along the fiber. On the horizontal axis, we have the times. And this is basically an amalgamated plot of 2.5 hours of raw DAS measurements, which would represent about 100 gigabytes of raw data. So that's what we actually want to store in the in our Exchange format. The color scheme on the right basically shows the intensity of the signal along the fiber, and you see, so these plots are, well, quite colorful, a bit of Van Gogh style art, but not often very meaningful. So what typically happens is that some filtering takes place to take out relevant signal for the type of thing you're investigating in the well. Now, here, basically, just to give you an indication of what we then need to store in these files. So, of course, we have an array that represents the data along the fiber. So on the right, you see basically a simple Excel type table where we show for each measured sample along the fiber in a single column. So that's basically corresponds with the vertical the vertical dimension or vertical axis, or depth or distance along the well. And then horizontally, we basically have the times. Now you could ask, why don't we store that all in say just a standard array and then we're done with it? Well, the thing is that because these interrogation rates are so high, and systems are sometimes have glitches, you may occasionally miss a scan. So one other thing we need to store in the as part of the data is also the measurement times. So basically, you need a combination of times and data arrays, and these are really huge volumes, which is why you will see later we store this in a so-called H5 file as a big, and we use these HDF5 files as a big container to store these data sets. A bit further on in the presentation, we'll also talk about the other data, because you need a representation of the instrument, the optical path, the settings of the system, etc. That will come a bit later. But first, we talk a bit about how we store the arrays. So to record a DAS measurement, a raw measurement, you both need to store the samples and the times, and you need to store the times because it's not guaranteed that you always have all the times collected. And remember, these systems can be on for days or months. So occasionally you may miss a sample. Okay, then now that's the raw data. These are huge volumes. Now, in many applications, you're not interested in the full spectrum of data, so not saying in the 10 kilohertz that you sample across an individual basically location at the fiber, which we call a locus in this standard that we defined. Often what we do is basically we filter out certain frequencies of interest because they correspond to certain features that we're looking for in the process that we try to monitor. So for example, if we monitor flow, then you're often interested in either low or high frequencies because they correspond to a certain type of flow. So what you see is basically that often we basically Fourier transform the data, and that's the interrogation system is doing itself on the using some very fast onboard processing capacity, and then it basically outputs a number of frequency bands from this transfer data. And in this example, you basically see a simple sine wave which is excited on a single location on the fiber. So on the left, you see that kind of schematically. In the middle, you see what it would look like on one of these so-called waterfall plots that you often see for DAS data. And then on the right, you can see that after you filter out certain frequencies. So in this case, you see two bands, one that has the sine wave in it, which is the red bar on the right. And the bottom one is the rest of the frequency spectrum, which doesn't include this. So that's why you see it missing. So often what we do to downsize the data, we process it into different frequency bands, and then these frequency bands are transmitted. And that's why we, apart from, say, a raw data presentation, we also have a so-called frequency band presentation. And if you basically would present the full Fourier or the full transformation spectrum, in case you use things like Gabor wavelets or some form of wavelet transform, then you can basically see it as a multi-dimensional array with many, many frequency bands. Yeah, so these are there. Here's a practical example again. So we see the same raw data representation as we saw before. And then on the right, you see say frequency band filtered versions of that. And what's interesting to see now, you can actually start to notice some additional features that you didn't, that were not straight away obvious from the raw data. So that shows kind of the power of filtering out certain elements. And then, yeah, typical examples, say for seismic, you would be interested in, say, 0 to 200 hertz. For microseismic, probably a little bit higher frequency, say from 0 to 500 hertz. For monitoring a gas lift valve, we often see frequencies that are a bit in the higher part of the spectrum. So that maybe you would use, say, some frequency bands above 1000 hertz. And say for flow phenomena in a well, you would often use the lower frequency. So that's why frequency band filtering is important. Yeah, so here you see again kind of an array representation of that. Now, of course, if you use a Fourier transform, then basically what you do, you average and sum over certain windows. So you have one time array representing the start times of these windows, and then all these frequency bands will basically have say a sample along the fiber. So that's the columns again, and then on the rows we see the different window times, and these can be different as for raw data, because often you not only downsample in by taking frequencies, but you also average over times to basically further aggregate the data. All these arrays share the same time, so you'll see that coming back a bit later in the presentation. Okay, so yeah, just high-level conceptual model, and yeah, just we're not going into all the details here. There will be a more detailed webinar later where we talk more about how do we now implement this in software. So here we keep it fairly high level. But what you see on the left is the three different types that we implemented at the moment in the standard. A raw representation, and then again the arrays are the data and the times corresponding to the data. And then for frequency bands, we basically have one set of times that's common for all the frequency bands. And then we also have a spectral representation, which is basically a three-dimensional array where the third dimension are all the frequencies in the array. And again, there we basically have the times which correspond to when you took the mathematical transform for each sample that you create. On the right, you see then how we store it in the so-called HDF5 presentation. So yeah, in one file, you could actually pack multiple arrays and array types. So that's why we use tree structure. And if you look very closely, you can see that we have, say, a node on the tree for raw data. Here at the bottom, might be a bit tricky to see. And there you again see we have the raw data times, and for raw data we also have trigger times in case you use triggered measurement. Then above that you see the process data, and on the process data we have two nodes, one for the frequency band data, one for the spectral data. Files can contain only one of these, so it's possible that you don't have a raw node or you don't have a spectrum node in the file if you only exchange the frequency bands. You also see there are some other elements, for example, we have a custom node under which you can store attributes that are particular for a certain vendor and something you may only want to communicate with your customer. And we also have a calibration object. And then at the top node, we have under that attributes that describe the acquisition. Yeah, and then here you see a zoomed-in version of that. So basically what I mentioned on the previous slide. So here you see this tree structure. So we have the acquisition at the top. And then under that, in the H5 file, there's certain attributes that are related to the metadata of the acquisition. So for example, things like the pulse rate that the interrogator used, the width of the pulses, the sampling along the fiber. But there's also other things like time zone, measurement start time for the overall measurement, and in case you have a triggered measurement, you also have the triggered time for that measurement in it. And then say for each of the subnodes, there are also attributes like, for example, the number of measurements. So we call that loci. So if you have, say, 1,000. If you take 1,000 samples along the fiber, then the number of loci would be 1,000, and then you don't necessarily have to start at the interrogator itself, but you could start storing the data for the measurement somewhere deeper in the well. So then you also define a start locus that's non-zero. And the same for frequency band data. There you would you may have a different output data rate, because you, for example, you output only frequency bands once a second or so. So that's something to store. And what you'll see if you look through the documentation there are a number of relevant attributes for each raw and processed data type that you can store in these files. And then here you see what it would look like if you use the HDF Consortium Java viewer. So you have a data array, and on the right you have a times array, and then in the viewer it shows up like a regular tree structure. This is just to give you an idea of how to look at data in case you open one of these H5 files. And so with that, I'll hand it over to Lawrence, who's going to talk a bit on how we then store the metadata and we use the XML representations for that. So Lawrence, over to you.
Yeah, can you hear me okay?
Yeah, sounds fine.
Is that okay?
Yeah, perfect.
Okay, just 1 second. Okay. So on this slide here, we're looking at the equipment and the metadata associated with it. And if you look at the boxes on the left, those are different XML files corresponding to the different pieces of equipment that we need to capture. This follows the same pattern as the DTS standard. So first of all, they're in green, and you can see the arrow pointing across. We've got the DAS instrument box. So there's a file and a schema for all the parameters associated with that. That's relatively simple. Then we have the fiber optical path, and this is a little bit more complicated. We're not going to go through the contents of the XML, but if you look at that sort of zoomed in box there just in the middle, it shows you what we're trying to track in that object, and it also, you can see these things in the sort of purple color or mauve color on the right. So what we call the inventory is the equipment. So that could be the cables, but also ancillary things that we need to know about, like connectors or the terminator at the bottom of the cable, and defects as well are part of the equipment, because these can all give artifacts on the signal that we're trying to measure. There's also the conveyancing as shown there. So we record how these cables are attached to the well or the pipeline, as the case may be. You know, for instance, they might be cemented in place, or they might be run in on a temporary survey, like a coiled tubing, effectively like a logging tool. And then we've got the network, which is the order they're connected in. So that's linear for these things, but we still have to record where this equipment goes and if it's still in place. For instance, a defect may appear after time, so it wasn't there initially, but then at a certain time we have to record that we're now seeing that. So that's really handled by the network and versions of the network. And then really importantly, we have what we call the facility mapping, which is, as you can see in the diagram there, you'll have a surface cable from the box to the wellhead in the case of a well. Then we go through the wellhead and then down into the well. So we have to know whereabouts along that length are we matching physical features of the thing that we're measuring. Otherwise, we just simply have these loci, but we don't know where they are. And so that's what's called the facility mapping. Whereabouts on our total length of optical path is the start of the well, the bottom of the well, and so on. Things like where's the packer. And then finally, OTDR surveys, which is like a sort of condition survey of the fiber. We can record those as well. So those are not the same as the DAS measurement. They're more like the condition of the fiber and allow us to do some of this mapping that I've been describing, so they can be stored. So that gives you the hardware, the instrument box and the optical path. And then this comes together in the DAS acquisition XML file. But these tables are also in the HDF5 that Wilfred was just talking about, the calibration table. If you think of that diagram which Wilfred was showing with the matrix of dots, time is running across from left to right, if you think of it that way, and then depth is running down from top to bottom. And what we need is, for each locus, each channel, if you like, of acquisition, is where is that in terms of measured depth, if it's a well, or what we call facility length, the distance along the pipeline, if it's a pipeline that we're monitoring. And so the fiber optical path combined with the setup of the acquisition, they come together to form basically a table of the locations of these loci in the physical facility. So that's a very important part of the metadata, because that really tells us what the system is that we're using to measure and where it is in real space. So if we go on to the next slide. Okay, now this is the architecture of how this data is transferred, and it's relatively complicated compared with traditional Energistics XML. But I mean, the reason for that is because of these huge volumes of data that Wilfred was talking about. So I'm going to start at the top. We've got there 3 boxes which are red color. So I've just been talking about those, the optical path, the instrument box, and what we call the DAS acquisition. Those are all XML files, and they're all about metadata. Really two kinds of metadata. One is what I was just talking about, the physical setup and the mapping of what we're measuring into the physical world, the real location along the thing we're trying to measure. And then the other metadata is the stuff that Will's talking about. For instance, the frequencies of a frequency band filtered array are available in this XML file, the start times, the stop times, all those sort of things. These files are very small. You can open them just with a text editor, and you'd see like the background to the slide there, you can read what's in them. So although they're designed to be machine readable, they're small enough to be very manageable. Now, if you think about the HDF files, you know, if those are gigabytes or even terabytes of size, they're really inconvenient to have to open up and find out what's in them. They're just huge files. So the concept is that these XML files tell you what you're looking at in the package without having to open the big files. And then there's a layer which is colored sort of light brown, where it says raw data, process data, FBE, and process data spectrum. These are what's called XML proxy files, and their role is really navigation. So the DAS acquisition file will tell you, okay, we've done this acquisition with these properties and this processing, and some of these acquisitions may result in many, many files, seismic type applications, for instance, and the triggering that Wilfred was talking about. There may be a lot of binary data files, HDF files. So these proxy files are there so that we can reference them, and those proxies themselves then tell us where to go and find the very voluminous binary data. So if you look at the raw data one, for instance, there are 3 files there shown, 3 leaves of that, and then 3 physical files. So you can just open those proxy files very easily. Again, they're very small XML files, and they'll tell you where to go and find the array in an HDF5 large file. So that's the concept of the architecture. And then at the bottom there, you can see a representation of the big binary HDF files. They might be gigabytes or even terabytes of these arrays of numbers. And you can see the little HDF viewer there that Wilfred was just showing. Some of the metadata is in those files, not all of it. These have the minimum metadata so that you can look at them alone and you can still work out what's going on. But for instance, they don't repeat stuff like the optical path or the instrument box or details of the vendor and all these sort of things. They're up in the XML, the full metadata, and there's a sort of cut down metadata just sufficient that you can, if you want to, open one of those files and get the minimum data you need to put it in context. And that's really just because sometimes these files can get separated from each other because it's not just like a neat, you know, Excel spreadsheet or something. These might be a whole disk on their own, and so being able to reassemble the data set is a very important requirement. And then finally, you'll see there's a grey ellipse drawn around the files which I've been telling you about, which are XML. These are all contained in one file, which is called an EPC container, EPC standing for Energistics Packaging Protocol. And that's actually just a zip file. So you can open it like the screenshot there shows with a zip application. And so it's just simply compressed and zipped together all the files that are needed to make the metadata part of the data set. So you actually end up with a manageable set of files. The whole transfer would be one EPC, which you can open up and get all these XMLs out, and then they all have links to each other. And then there'd be a package, one or more of these large HDF files with the arrays in. So that actually follows the pattern of RescueML. Right, so now just turning from the technology, yeah, we can go on to the next slide, that's fine. Turning from the technology to the process by which this was developed. I don't know if you've got the next slide. Yes, I can see it now. This just gives you a bit of information about who's been active in this and the timeline. So the scope here was initially conceived to build on the DTS PRODML, which is also data fiber optic path. And so, as I said earlier, the idea of having the optical path and the instrument box and the data as sort of separate files and separate data objects is shared with DTS. The volume of data is even more here. So unlike DTS, we had to go to these binary files, HDF. DTS doesn't need that because the volume of data isn't so high. But the concept was build on the DTS model, deal with the raw data and the processed data, the frequency bands and the spectrum that we've been hearing about, and come up with a standard. And this was first proposed back in June 2014. It was proposed by Shell, no doubt for the business reasons that Wilfred outlined earlier on, the large costs of dealing with custom implementations of this transfer from every supplier and every application. The work started early in 2015 and coincided with the development of PRODML version 2, which was actually moving from a standalone PRODML to that integrated common technical architecture which Jay was talking about at the start of the presentation. So PRODML version 2 using these same data objects and architecture as WITS-ML, RescueML and so on. So that was all being done in parallel, and that work was finally finished at the end of 2016, and the version 2 published at that time. Now, the V1.0 of anything may not be the last word, so we then had an adoption project starting January 2017, but took a little while to get cranked up because we'd only just published the version 1 schema. Several of the member companies used that standard then in real-world deployments, including Shell and some of its suppliers. And out of that came fairly small number of improvements that could be made. So they led to a version 2.1, and that was released as a draft in August last year, so about 6 months ago. And that was based on the adoption experiences. So a few things were changed, but the basic concept didn't change. Attributes, really, to make some of that navigation through the metadata easier and so on. So that is the release that we think, based on this real-world experience, can be adopted by industry, and we're aiming to have that released in a sort of final form. It's out for review now for anybody to comment on, members or non-members of Energistics, by the Q2, so during the next quarter. But it should be stable. Nobody's giving us any feedback that it needs to change. So that is the transfer as Wilfred has been outlining, and latterly myself with this metadata. Now, a more recent requirement, which is slightly aspirational at the moment, is streaming of data. And that's what this slide deals with. I'm going to hand back to Wilfred to just explain the business case of that. But this is a project that we have live. Some work has been done, but there is not yet a standard for the completed, but this is a work in progress. So I'll hand back to you, Wilfred, to talk about the business case for this and then wrap up with where we are with it all.
Yeah, thanks, Lawrence. Yeah, so basically what we showed and what has now been released as PRODML version 2 and with version 2.1 containing some updates that are currently under review is basically a data exchange standard for these large files. But where we really want to move to as an industry is to have this data available in real time over distances. And then depending on the application, you can either transmit, say, a small amount of data. So for example, for some of the frac jobs that operators are now performing in the field, we often already use live data to assess the fracs, and then we typically use something like TeamView or so, or some kind of screen sharing to assess that. But it would be really nice to have that, say, live streaming in a database and then having that available for remote users so that you can really make use of expertise of folks that are, say, in some of the R&D centers or in some of the support centers for either vendor or operator, or in academia that can actually look live at the data being collected at the well. An added benefit of that is, well, first of all, you don't have to travel to the field anymore. You can basically have your expert staff dialing in to the well to give recommendations on things to change, etc. And also it's a lot safer because you don't have to have all these folks on site, which is a huge advantage. Yeah, so there are different types of use cases. So for frac monitoring, but also for real-time flow. We have done some of that work already a few years ago where we were streaming that into a portal. And eventually, if the networks permit, you could also see use cases where you basically want to stream the raw data from the field into a central cloud server. Typical sizes are displayed here. So for frac work, it's probably about 100 kilobytes per second. For flow, it can be a lot smaller because you just sample it, say, every few minutes. And for all data sets, you would look at huge volumes up to 100 megabytes per second. And for that, we basically we've defined a charter for a new project. The idea would be to use the Energistics transfer protocol. And one thing we're looking for is actually, say, a customer operator and a number of suppliers that would have a real live example to test it on. That was actually one of the nice things in the Exchange Standard project, is that we had real data to try this on as we go. So that's why this standard is also seeing some uptake at the moment, is because we tested it on real data sets, so we could show on the project itself that the standard was actually suitable to transfer data, and it also gave us some confidence and the participants that we could roll it out in a wider community for real applications. And at the moment in my company, for example, when we acquire DAS data, we ask vendors to produce that in the PRODML data exchange format. So next step will be to look at real-time transmission and then streaming data and we can use then the Energistics transfer protocol, and you can basically see that as kind of Netflix for data streaming. So that's work in progress, and we're actually looking for an example where we can develop that on. Okay, then maybe to wrap up the formal part of this presentation. So a few key takeaways. So Exchange Standard has been defined, and it was released already version 2.0 in December 2016. An adoption project was run in 2017-18 where data was exchanged between different parties, both service provider and operator. So yeah, as I said, in my company, we already use this to transfer huge data sets of up to terabytes to basically exchange between ourselves, vendors, and interested parties. When we were doing that adoption project, there were a few things that we thought could be streamlined. So we made some minor modifications, and they will be published in Q2 of this year, and it has been out for review for a while now, since Q3 last year. And basically, the adoption team is still meeting about every other month in one of these virtual meetings, a bit like this webcast, where we basically discuss use cases and also exchange information where we are with the implementation of PRODML. Now, as I mentioned, clear benefits for using a standardized approach. We've seen over the last years that DAS is really taking off, particularly in unconventionals. And there are often many parties involved in analyzing the data for a single well, so it's actually no-brainer to have an exchange standard. And as I mentioned earlier in the talk, just in my company, we see clear benefits from saved development costs for not having to write custom software, faster time to analyzing the data and taking decisions, and less time wasted by research and data management staff to basically convert data sets. And also, as you saw on one of the first slides, I mean, there's a large number of DAS applications that you can use on fibers, whether it's on wells or on pipelines. It's still growing, so there's clear benefits to having a standardized approach. And last but not least, we kicked off a streaming activity which will look at the Energistics transfer protocol. That's open for participation, so that just started for folks that are interested in taking part in that. Yeah, with that, then I'd like to hand it back to Jay or to Jenna to close this out and to go to Q&A.
Thanks very much, Lawrence. Really appreciate you and Wilfred giving this presentation, and Jay for the intro. We're now looking at questions. If people have been, we have so far none submitted by anyone in the audience. As mentioned, you have this Q&A button as part of the Zoom screen. So if you click on there, you can type in a question and we will address it immediately online.
I guess can you hear me okay?
Yes.
I guess while we're waiting for that, there's a little interesting fact that I would point out just to entertain people while we're waiting for them to type questions. Wilfred was showing in the very beginning that we define these locations along the fiber that he called loci or loci, and they said we have an array that we store the time in which it's the time to reach each of the loci. And an interesting fact that I didn't know until we embarked on this work is that you would assume that why would you need to do that? Because you know the speed of light, and you know, therefore, if you get a reflection at a backscattering at a certain time, then that you must have that correlated. But the truth is, in a fiber optic cable, light doesn't travel at the same speed that it does in a vacuum. So we in fact have to measure the time it takes for light to come from specific distances. So that's the array that we're actually storing, is the measured time along the fiber as installed. And so that turns out to not be simple high school physics. So
we have a question here about the physical spacing between loci along the fiber. Lawrence or Wilfred, either of you want to take that?
Yeah, so it's not a function. Well, the physical spacing is basically a function of how fast you sample the backscattered signal. So there's two things to distinguish. It's the sampling of the signal itself along the fiber, and it's the pulse rate. So for each pulse that you shoot in a fiber, it takes some time, even at light speed, to go to the end of the fiber and then to record the backscattered signal. So that sampling within that time frame of the backscattered, that's basically what determines the physical spacing between the loci. And then the number of pulses that you shoot in the fiber, that determines the overall data rate of the system. So yeah, and in simpler form, I mean, they're more complex schemes, but basically you need to wait till the pulse has gone to the end of the fiber, and also you have then the same time to wait to record all the backscattered signal, and and basically how long you have to wait, that determines on where you are measuring on the fiber. And by doing this, say 1,000 times a second, and then if typically say the signal is coherent on the backscatter, so as long as the fiber doesn't change it, so if there's no strain applied, and the signals will look the same on a single location. As soon as you apply strain or another physical variable, that response changes, and that's how you measure this basically.
And there ends up being a relationship also between the length of the fiber and sort of the windows over which you're measuring the backscatter. So on a, if it's somebody trying to measure along a fiber laid along a pipeline, this may be 20 kilometers long, then you end up, in order to get the backscattered light returned, enough backscattered light returned to actually see what you're looking for, whether that's temperature or amplitude, you end up having to have more light over a larger distance, as a larger length along the fiber. So there ends up being a relationship also. It's easier to do a shorter fiber than a much longer fiber, but wells aren't normally so deep.
Yeah, and you can also sample with higher rates if you have a short fiber in a shallow well. And then the typical spacing is, yeah, I mean, in initial system were like 10 meters. These days it goes up to half a meter or even smaller. Depends a bit on the make of the system and but we can basically sample up to a meter, half a meter. Some cases closer. Depends a bit on the vendor and the specs of the system.
Yeah, but there are some use cases. I mean, the pipeline industry, their use case is if they've laid fiber along a new pipeline for control purposes, like to control valves and things, it just turns out we can reuse that same fiber for doing DAS along the pipeline, looking for tampering or leaks or whatever. But they have this problem that those fibers are quite long. And so they're not able to, mankind isn't yet able to shrink the interval down. So you're gonna know there's a sound, but it's within a few tens of meters rather than getting it down to a half a meter.
Yeah, but there are some tricks to go around that. But that at least so vendors are working on using interesting schemes to get to sub meter resolution, or in the case of pipelines, say to get closer distance, let's say tens of meters.
Yep.
Okay, are there any further questions from the audience? Who would like to take this?
Yeah, so that's a good one. That's actually so a question from Graham. How are definitions of the 0 point for depth or length measurement illustrated in the metadata? Using drill floor height for the open hole comparison isn't always applicable in other applications. That's correct, and that's why we have this calibration object, and we have a detailed definition of the optical path. What you do for a typical thing that commonly is done by operators or service providers is that you insert, say, a known location in the data. So, for example, we often do a tap test around the wellhead, and then we can look at the data and see exactly at which locus or which measurement point along the fiber we have the wellhead, and then that way you can correlate it back to drill floor height, etc. It's I can also tell you that's one of the things that was a bit more tedious in defining this standard, because dealing with say to bring it back to where are we relatively to the drill floor, that's of course a bit of a tricky thing, not only in DAS measurements but in any type of wireline or related measurement.
Following question.
Yeah, there's another question there, Philip.
Yeah. I don't know who wants to take an answer to that. Maybe this is more something for Jay.
So how do you plan on storing this data? Yeah, so as I said, a transfer of DAS data, realistically, for what Shalom and what Wilfred experiences, is you should have a little zip file, which is that EPC file, and then you probably won't have a single HDF file because a DAS job is so large that in Shell's experience, you got a box full of 3 terabyte drives. And so you get 10 3 terabyte drives, each of which has part of this sort of virtual large array. and then you have the little metadata that contains information about the optical path and so forth. So managing that for anyone is going to be challenging. But what we believe will happen is because the little EPC file is quite small, it's not much of an issue. But you have to decide how you're going to manage a data set of 30 terabytes, and whether you're going to try to copy that over the public internet, whether you're going to do something on premise. I know 2 operators, but I don't know if what they're doing is considered proprietary or not. But I know of 2 operators that have built large data centers specifically with petabyte scale storage to be able to store and analyze this data, and they treat that like it's a sort of an internal cloud, because copying this data over the public cloud would just take weeks, basically. So that's there is no specific kind of database, because you wouldn't want to put a 30 terabyte blob into an Oracle database, or a 30 terabyte anything into any of the NoSQL databases, and then you'd have tens or hundreds of those depending on how many wells you've been analyzing. So the data management aspects of it are quite challenging. Do you want to talk about what Shell does, Wilfred?
So I mean, what we did before, so we developed with one of the vendors actually a cloud solution where we stream frequency band filtered data into the cloud, and then that's what kind of live streams in it, and then so that already reduces the data volumes by a factor 1,000. As Jay mentioned, others are looking at streaming the full data in, and then probably not the full 10 or 50 kilohertz, but subsets of that. And then, of course, bandwidth is an issue. I must say, the experience we have with some of our live wells where we use this real-time data with the database and the cloud option that the vendor provides us actually worked quite well. So, I mean, it's data transfer rates were actually suitable to transmit it over a cell phone. So I think what you basically have to do is, depending on the application you want to use, you have to work with your providers to see what kind of data management solution you need. I mean, ideally for something like microseismic data, what I would really like is that, say, the systems at the well site extract the events a bit like you do with geophone microseismic, and then transmit the event locations over, plus say the coda of the microseismic recording for the PRODS waves, and then and that would be a fairly manageable data set. And indeed, there's ongoing work in industry to see how that can best be solved, and that may vary per operator.
And it may be worth saying that there, if microseismic data is what you're interested in, there was an effort in the context of Energistics 5 years ago or so, even longer ago than that, of a community of people that were interested in a standard for microseismic data, which would have provided an infrastructure to let you manage that information. But when the downturn came, key people got different jobs, and so and that kind of went away. But if there is a community that's interested, we would certainly consider revisiting that if there was a sufficient community.
Yeah, and then one thing maybe that I would like to say about the data volumes, I mean, you should not be scared by the terabytes of raw data, because for most applications you only need a small subset of that. So it's really in the end an engineering question of how much you want to transfer and what, and it takes some experience to get to that. But it's not that for each application you need to deal with a terabyte of data.
Okay, well, thanks for those answers. We've come up against the time limit of this event, so I want to thank certainly the people who have presented, and also the people who put in questions. Interesting insights there. As mentioned earlier, this has been recorded, so it'll be available for review or for sharing on our website. Give us about 24 hours for that. There is a survey. As you close your attendance, you will be presented with a survey. If you could quickly answer a couple of questions, that would help us. And as I think Wilfred mentioned, we have another webinar on the more technical aspects of distributed acoustic sensing that will be in the month of April. Look on our website. We don't yet have the details to join the meeting, but those will be posted within a couple of weeks or so, well ahead of the event. So thank you again for attending, everyone. Wish you a pleasant end to your day, and look forward to seeing you soon on another of the Energistics webinars. Thank you.